Thanks for being here. My name is Alex Leong. I'm a software engineer at a company called Buoyant. We're the creators of the Linkerd service mesh. I've been one of the core Linkerd maintainers since the beginning, so I'm a little bit of a service mesh enthusiast. But this talk is going to be about network security kind of in general, and service mesh can be one part of that or one potential solution to that. So I'll try to keep my service mesh bias to a minimum, but I'll also try to bring you along and show you kind of why I think service mesh is maybe a good choice here, at least in certain circumstances. You can find me on GitHub or on the Linkerd Slack if you want to come chat with me. Or I'm going to be here at KubeCon all week. I'll be at the Linkerd kiosk in the project pavilion if you want to come and chat. So this talk is called, it's 2025, why are you okay with an insecure network, exploding head emoji. This is kind of a weird and long name for a talk. And in retrospect, I think maybe what would have been a better name is an even longer one, which is, should you be worried about security and what can you realistically do about it? And what I like about this title instead is that the different parts of the title kind of map to the different parts of the talk. So I'm going to start by talking about the insecure network and what does it mean for a network to be insecure and what kind of things should we be worried about when we're thinking about network security. I'm going to talk about these three pillars of network security: confidentiality and integrity, authentication and authorization, and what are some different ways we can implement these and make sure that our network is secure in these various different ways. And then I'm going to wrap up by talking about operational concerns because, unfortunately, we live in a reality, and we can't just have the perfect security for free. There's always some kind of trade-off or cost-benefit we have to think about. OK, so starting off, we'll talk about the insecure network. Like, should you be worried about network security? Spoiler alert, yes, you should. But when we're talking about an application that's running in Kubernetes, it behaves very differently than kind of a monolithic single process architecture where you have different parts of your application which are calling other parts of your application through things like function calls. And that's all happening in process, in memory. When we move to Kubernetes, now we've got all these distinct units that are running as pods, and these pods are talking to each other over the network. And so there's typically like TCP connections. These might all be in one Kubernetes cluster. They might span multiple Kubernetes clusters. You might have some pods in network, some pods in cluster, some pods running outside on VMs or on bare metal machines. But all that communication that's happening between them is all going over the network. And so suddenly you have this much larger surface area that you have to care about that you never had to worry about when it was all kind of in one process. And so when we think about those connections between those pods, if we're looking at the OCI security model or OSI security model, we've got all these different layers. We're typically talking about TCP/IP, which is layer 4. And so that gives you some guarantees in terms of reliable delivery and in-sequence delivery of packets, but it doesn't really give you any kind of guarantees in terms of security. And so that's kind of what we mean when we say that the network is untrustworthy. Layer 4 doesn't have any security mechanisms baked in, and if you want to add those, you have to add them at some layer higher, some layer above layer 4. So network security, one of the things that you want to think about is that you want confidentiality. So if you've got two parties that are talking to each other over a TCP connection, you want to make sure that anyone else who's on that network can't look at those packets and read those bytes and snoop in on that conversation. That should be private between A and B. We also want integrity. We want to know that that data has not been tampered with. So when A sends to B and B receives those bytes, they want to know that that is actually the bytes that A sent and it hasn't been intercepted in the middle and transformed or spoofed or something like that. We want some form of authentication. We want to know who the other party we're talking to is. If someone says, hey, I'm your web front end and I'm calling your database, we want to know that that's actually true and that's not somebody kind of forging that identity. And then with that in place, once we know who we're talking to, we want to make some kind of decision about whether they should be allowed to have access to that or not. So some kind of authorization that says this party can access this data or this endpoint, and this party cannot. So if you don't have any of those kind of pillars of security in place, then a bad actor on your network can do all kinds of really, really nasty things. They can listen in on any connection. They can snoop that data and read it. If there's PII or sensitive data of any sort in there, they can just read it. They can potentially do man-in-the-middle attacks and tamper with the data in transit. They can make any connections to anything in your Kubernetes cluster and say, hey, I'm allowed to be here, I'm allowed to do this. They can read sensitive data, they can perform sensitive operations. They can basically do anything. So you might think, okay, well, that's fine, because there's no bad actors on my network, not a problem. Probably not true. But what do we mean when we say bad actors? So bad actors, they could be an external bad actor. They could be someone who has somehow gotten SSH onto one of your nodes, or somehow gotten access to your cluster. But it can also be something internal, right? It can be some software that you are intentionally running on your cluster that has security vulnerabilities that allow for remote code execution, for example. Or maybe if your software doesn't have these vulnerabilities, maybe some other software that you pull in as a dependency does. So you're unknowingly pulling in those vulnerabilities through your supply chain. And there are humans that have access to your clusters, and they are vulnerable to social engineering, phishing. They may be intentionally or unintentionally doing something bad. And in all of those cases where we had an internal bad actor, those were all things that were supposed to be there. They were supposed to have access, but they were doing something that they weren't supposed to do. And so when we think about network security, what we really want to think about is limiting the blast radius of someone who's on there, so that they have the least access they need in order to do their job. But if they do become compromised, they can't kind of do anything. They're limited in the damage they can do. So limiting the amount that they can read or modify, or the actions that they can take, really applying the principle of least privilege. So the first pillar I want to talk about is confidentiality and integrity. These two kind of go together because typically they're achieved in the same way. And what we want here, just as a reminder, is we want nobody to be able to read that data in transit other than the party that is supposed to be accepting that data, and no one to be able to modify that. And typically this is done by adding transport layer security, TLS. So we add encryption onto that connection. This is also sometimes called SSL or HTTPS, although those are slightly different. And so if we have the pod Alice here talking to the pod Bob, if we encrypt that connection with TLS, now those packets are encrypted. Anything going across there can't be read by a third party. Any third party kind of listening in on that connection won't be able to decrypt those bytes, won't be able to modify them because they don't know what they're looking at. So even if you have some other compromised system on your network, that connection between Alice and Bob is secure. So there's lots of ways to add TLS into your application in Kubernetes. You can use something like IPsec or WireGuard. Those are typically implemented by using a CNI plugin. So this is very easy to set up. You just tell your CNI plugin, hey, do TLS between nodes, please, and it does it, and you're good. You can also implement this using a service mesh like Linkerd or Istio. In that case, there's going to be some kind of proxy running somewhere that's going to intercept your connections and upgrade the connection between them using TLS. So it'll add TLS onto those TCP connections when it goes from one proxy to the other. Or you can just kind of build TLS into your application. Anytime your application is going to make a TCP call, instead of doing a plain text TCP call, you could instead use a TLS call. So that's kind of the easy one, asterisk. So we'll come back to that, but for now I also want to talk about authentication. So when we're talking about authentication, we're asking the question of if we're receiving a connection, or if we're establishing a connection even, who's on the other end of that connection? And how do we know that that's true? And with just TCP IP, all we get back is the IP address. If we establish a connection or receive a connection, all we know is, hey, we're talking to 10.24.0.210. Who is that? I don't know. So in Kubernetes, there's this concept of network policy. And so network policy is this Kubernetes resource that kind of controls which pods can talk to which other pods. And this is typically enforced by a CNI plugin. And it does this authentication using the pod IP addresses. So if you look at what a network policy resource looks like, it's very simple, but we just have a pod selector there that says which pods that this policy applies to. In this case, it's Nginx. And another selector that says which pods have access to call that. And so this says if you have the access true label, then that means you're allowed to talk to Nginx. But you may notice that this seems like it's doing authentication by pod labels, I just said a second ago that we do authentication by pod IP. How does that work? So to kind of break that down, suppose we are this pod called Alice here, and we're receiving a TCP connection from this IP address. We don't know who that is or what it is. But we've got our CNI plugin that's going to enforce network policy for us. And what that plugin is doing is it's querying the Kubernetes API, and it's pulling down a list of all the pods in the cluster and what their IP addresses are and what labels those pods have. And it's using that to hydrate this index, which maps pod IPs to which pod it is and what labels they have. So the CNI plugin knows that when we get a connection from 10.42.0 to 10, that's actually Bob. Bob has these labels. And at the same time, the CNI plugin is also watching all the network policy resources in the cluster. And so it knows, what things should be allowed and what things should not be allowed. So it can see in this case, hey, if we should only allow things if they have the access true label, this connection coming in, because I can look it up in my little cache here, I know that that's Bob. I know that Bob has the access equals true label. So I know this connection should be allowed. And so it will set up the routing rules so that that connection goes through. So this is IP-based authentication. We use the pod IP kind of as the starting point of this authentication scheme, but then we use this index of IP to pod mappings that's hydrated from the Kubernetes API in order to determine whether the pod has the appropriate labels to be let through. But what happens if this cache gets behind? This is a cache that's populated from watches on the Kubernetes API. It is eventually consistent. And in fact, if that cache is delayed and there's IP reuse in your cluster, this can result in really serious security vulnerabilities. If one pod that has a certain amount of access is destroyed or deleted, and then another pod comes up with the same IP address, if that cache is behind, the CNI plugin won't know the difference. It won't be able to distinguish them. And so that new pod will kind of get all the same privileges that the old pod had, regardless of whether it's supposed to have them or not. And so there's a really nice demonstration of this by Lin Sun, which you can watch on YouTube. And in fact, any IP-based authentication scheme can have this problem. IP addresses are not a guarantee of identity. Just because you happen to have a certain IP address doesn't mean you necessarily are who you say you are. But if we're using TLS for confidentiality, we can also use that for identity. But whenever you have a TLS connection, there's this handshake that happens at the beginning where the two parties establish each other's identities. And this is cryptographic. It's a cryptographic handshake. It's not based on the IP addresses. It's based on private keys that are only known to each of the parties. And so this is a lot more robust because it's not depending on which IP you're assigned. It's based on something that's private that only you know. And when both parties are authenticated, the client authenticates with the server authenticates with the client. This is called mutual TLS or MTLS. So if you're using something like WireGuard or IPsec in order to get TLS, the kind of downside of that is that only the cross-node traffic is encrypted, which means that rather than getting pod identity, you get node identity. And so if you have one pod talking to another, well, those pods are running on nodes in Kubernetes. But in terms of identity, the identity you get on that TLS handshake, all you know is that the node that it's coming from. And this is not particularly useful because lots of different pods are co-scheduled on the same node. Just because two things are on the same node doesn't mean they should have the same accesses. This is not a useful form of authentication. What we'd rather have is something like workload identity. We want each workload to get a distinct MTLS identity. And typically, workloads are kind of one-to-one with service accounts, in many cases. And this is what's implemented by service meshes. So if you're using a service mesh for MTLS, each service account gets a distinct cryptographic identity. And so if you're talking, between Alice and Bob in the context of a service mesh, you're going to have these proxies that are kind of protecting that connection. And those proxies are holding on to the private keys for each of those parties, and they can authenticate each other, do MTLS, and they know who's who, and it's all secure. Or if you're kind of using a different service mesh deployment where you're using ambient and you're using waypoint proxies instead of sidecars, it's the same thing. There's just potentially more pods behind each waypoint proxy, which means that each of those waypoints is now holding a lot more private key material, since they need to have the private keys for kind of every pod that's behind them. So it's the same model here, but there's a little bit of a bigger blast radius. If those proxies were to be compromised, they're holding a lot more private keys. There's a larger surface area there. And then finally, you can just do away with service meshes and CNIs altogether and just do this yourself. There's no reason why the application can't simply make these TLS calls itself. They have to manage their own private keys, do all that. But then you don't have sidecars, you don't have CNI. It's just all baked in. And this is great, but it's only as secure as those private keys are, which means that you probably want bounded lifetimes on those keys. You probably want to do key rotation. You probably want to do certificate change management. It gets complicated, especially to do this properly. And so there's lots of solutions out there that can help with this, like Cert Manager. But to kind of manage this properly in your application it's quite challenging. Okay, so there's a lot of different ways to do authentication. You can do something that's network policy based, which uses IP, but it's kind of susceptible to these fundamental insecurities when you're using IP as a form of identity. Or you can do something cryptographic using MTLS, using WireGuard or IPsec or a service mesh, or building it into your application. And this is cool because once you have authentication, you can do authorization. And so if we look back at that network policy resource that we looked at earlier, this is really describing the authorization policy. It's saying that these pods here, matched by this selector, authorize connections from these other pods matched by this other selector. And if you're doing this in a service mesh, then each service mesh typically kind of has their own configuration language for specifying authorization policy. So this is what the one for Linkerd looks like. Very similar. There's, these pods authorize connections from these pods. You can see that in orange there, that's a service account that represents the identity. This is the one for Istio. It looks very similar. Again, authorization by service accounts. And this is saying that this is authorized to talk to this. And so if you have authorization policy in place, it's a really effective tool for limiting that blast radius of a compromised system, because you can say this workload or this identity in my cluster is only allowed to access certain endpoints, certain methods, certain services. And the more restrictive you make that policy, the smaller that blast radius is going to be if that service does become compromised. So again, this is just an example of the principle of least privilege. Now, unfortunately, we can have kind of the greatest security system that we can imagine, but putting into practice is not always so simple. There's a lot of barriers to having good security. You can have different competing priorities, lack of experience or staffing, and there's like an operational cost to putting these things into production. You have to maintain them ongoing, and that can be a real barrier. And the best security system is one that you'll actually use, right? So you want something that you can maintain and something that you can operate. So if you were to kind of rank these different options from least operational cost to most operational cost, I think this is kind of roughly what the order would be. Nothing has the least cost, at least up front, although you may find that that cost grows when you have incidents, all the way over to the other side, which is building it yourself and kind of rolling your own. So if you have no network security at all, you're wide open, bad actors can do all kinds of nasty things, probably not great. If you're using something like IPsec or WireGuard, you get TLS, so you get confidentiality and integrity, but you don't get any kind of authorization or authentication, or at least not one that's useful. And so while bad actors can't necessarily snoop on other connections, they can still initiate their own connections, and they can be on the network and impersonate people and do bad things. You can use something like network policy, which is going to give you that authentication and authorization, but it is IP-based, so it is kind of fundamentally vulnerable to this idea that IPs are not a reliable form of identity compared to something that's cryptographic. You can use a service mesh like Istio or Linkerd, which is kind of going to give you, I think, much better properties in terms of confidentiality, integrity, authentication and authorization that are cryptographic and secure. And there's kind of a few different choices between deployment models here, sidecar and ambient. Or you can kind of build it into your app and do this MTLS management yourself. But again, this is going to be very complex and hard to manage. You have to think about key rotation, certificate chain management, and just making sure that you're kind of doing everything correctly. You have to think about what ciphers you're using. There's a long list of things that you need to get right in order to do this yourself. So I think this is like the correct order in terms of least cost to most cost operational, but I don't think this picture is quite to scale. I think that if we wanted to scale it, it would look something more like this, right? Where building things yourself is going to have a much, much higher cost than any of these other solutions. And because of the way that this is laid out, I really like how Service Mesh here is positioned as something that gives you these really nice security properties, kind of more so than any of these other solutions, but at a really, really small operational cost compared to doing it yourself and building it in your application. So I think it's kind of a really nice trade-off here in terms of what you get versus what you have to pay operationally. So yeah, I mean, the bottom line here is that the best security is the one that you're going to use. So you have to think about that trade-off in your environment and what kind of works for your organization and how you want to put into place something that is going to be effective for you. That's all I had for this talk. Thank you for attending. I also just need a few minutes to plug that Linkerd just announced support for MCP. So if you're interested in running MCP workloads or you're already running MCP workloads and you want a service mesh that's kind of aware of that, you can sign up for early access or come find me anytime through the conference, and I'd be happy to chat more about it.
Do you prefer sidecar or sidecar-less solutions when we're talking about service meshes?
Yeah, so I work on Linkerd, which is only has sidecar mode, so I'm very pro sidecar. And the reason for that is because of the security properties it has, right? You've got a one-to-one mapping between proxies and pods, and so you have this really tight security boundary where if that pod becomes compromised, all that becomes compromised is that pod. Right? It has that very limited blast radius compared to something like Ambient, where you've got one waypoint proxy, which is fronting a large number of pods. So it has all that private key material that it needs to do that is all kind of commingled there. So you've got basically this multi-tenancy. So I think sidecars are a much nicer model for their security properties.
So it's a matter of trading performance versus the blast radius of in terms of security?
Yeah, I think that's one way to think about it. I mean, we've also spent a lot of time really optimizing the overhead of the Linkerd proxy. So unlike with Envoy and with Istio, we don't use that proxy. We use a Rust proxy for Linkerd, which is designed to be very lightweight and is designed to be run as a sidecar.